today we have the pleasure of presenting bugs for buckets, active defenses against stealing encoders. So recently, machine learning applications have become really ubiquitous. Numerous companies have been working on developing their own machine learning models. Many of those companies then make those models available through an API, mostly to profit from this solution. And for the case of supervised model, this works in the following way. A user sends a query, for example, an image they want to classify to the server. Then the model returns an output, for example, a class label in this case. And this class label is returned to the user. However, recently, a very hot topic in machine learning has been unsupervised or self-supervised learning. And through those methods, we can train really powerful encoder models, like, for example, Dino. Those encoder models work in the following way. They extract the most important features from the input, and in turn, those features can be later used for some other task, which we will call a downstream task. So in the case of an encoder model available through an API, the mechanism is the following. So a user sends a query to the server, for example, an image from which they want to extract important features. And then the encoder calculates a high-dimensional representation containing the most important information about the input. And this representation is then returned to the user. And they, on their side, can do whatever they want with this representation. For example, solve a classification downstream task using their own developed models, but also use it for numerous other purposes. And why do people even use APIs? This is because, as you know, training models, including encoder models, is extremely costly. So you have the time and money needed to collect and clean data, to tune the hyperparameters, and of course you need to have hardware to run it for training and for inference. And for example, the cost of, as Adam already said, the cost of training GPT-3 was around $12 million. And this high cost of training encoder makes the concept of model stealing tempting. And model stealing is a kind of attack against machine learning models in which the attacker aims to train a stolen copy of the model using only a fraction of resources needed to train the original. And because of that, model stealing was ranked among one of the most severe threats against machine learning models. So how does stealing an encoder model works? We have an attacker which selects a data point, sends it to the encoder API. The encoder model calculates the representations and returns them to the malicious attacker. However, the attacker does not want to solve any downstream task. What they want to do is to gather information about the encoder and train a local stolen copy of the victim model. And what's important is that stealing encoder models is query efficient. So the more queries you use, the better results you will get. And existing defenses for supervised models are not adequate for self-supervised models like encoders. In more detail, I will now explain one of the methods to steal an encoder model. And this attack method utilizes Siamese networks. We have an input image. We apply two different sets of augmentation to that image. For example, one can be black and white, and other can be rotated. Then we pass one sample to the victim model, which we want to steal, and the other to our local stolen copy. We calculate the representations, and we train to maximize the agreement between them. And in this process, we can train a local stolen copy of the victim model using only 1/5 of the resources needed to train the original. So as you see, this is quite worth to do it. And obviously, as an API provider, we want to protect our precious model against stealing attempts. And up till now, the defenses for encoder have been only reactive. They basically boil down to ownership resolution, and through techniques like watermarking, in which you add a pattern to the model weights, model output, you could later recognize if a particular model was a copy of the model that you owned. And this has really obvious negative sides. I mean, you can only do it post factum, and then you actually have to claim that this particular model is a stolen copy of your victim model. So if you never knew about the copy, you wouldn't even apply this tool. And what we propose is an active defense against encoder stealing. And how does our solution work? So first, let's start from a couple of very important observations. So we notice that queries from legitimate users occupy a single region of the latent space. So that means that the representations that the users want to use can be mapped to a particular location in the latent space of the encoder. And this is because they utilize the encoder to solve a particular downstream task, like, for example, dog classification. However, the attacker, in order to steal the encoder, must use diverse queries and query the entire representation space to succeed. And this difference between legitimate users and the attacker is the basis on top of which we built our defense mechanism. And our idea is that we divide the entire latent space into buckets, and for smaller number of buckets, we have a low cost associated, which is not bothersome for legitimate users. However, as the number of buckets that are occupied increases, then also does the cost. And in this way, we make the stealing of the model too costly for the attacker. How do we do it in more detail? So to divide the latent space of the encoder, we use the local sensitive hashing algorithm, LSH. And in principle, we apply a hashing function to the representations. And like in a standard hashing algorithm, those representations are then assigned or mapped to possible hash buckets. And those hash buckets are the buckets from the previous slide that we want to monitor. And let's take a look on how the coverage of the latent space, so the number of buckets occupied, changes from different data sets or different behaviors. So at the bottom, you can see SVHN, Cypher10, Fashion MNIST data sets, and they represent downstream tasks that legitimate users may want to solve. You can see that the number of buckets rises with the number of queries, but then it saturates. However, this model was trained on ImageNet, querying from the entire ImageNet dataset, which could be used to train a stolen copy, results in a steadily increasing number of buckets, which is much higher than for legitimate users. And one may ask if this mapping of if this measurement of the latent space coverage works only for the data set on which the model was trained. I mean, the answer is we get high coverage not only for the data set on which a particular model was trained, but in general for diverse queries. And here you can see how the increasing number of queries results in increasing number of buckets for data set like ImageNet and Lion, which both could be successfully used to steal an encoder. Another question you might have, what happens if I want to use part of a complicated data set? For example, what if my downstream task is classification of dogs from ImageNet? Will I also get a high coverage of the latent space? And the answer is no. When you only utilize part of the data set, it does not result in a high coverage of the latent space, and there is still this region that separates the attacker and legitimate users. Now that we have the estimated coverage of the latent space through the number of buckets, we map this fraction of buckets covered to a cost. And we want this cost to be negligible for legitimate users and very high and very painful for the attackers who want to steal the encoder. The encoder. And the cost that we decided to go with to prevent stealing is, in this case, adding noise to the representations returned to the user. So with high number of buckets comes high noise added to the representations. So overall, this solution for adaptive defense framework works in the following way. First, the model calculates the representations for the user queries. Then we estimate the coverage of the latent space using our buckets from the LSH algorithm. Then we map the number of buckets to a particular cost, expressed as noise that we add to the representations returned to the user. And here one might think, what about a smart attacker? What about an attacker which sets up multiple accounts and just queries, using a few queries from each of them to always get those nice and noise representations? Would that work? And the answer is no, because we prevent it using transformations. So before returning the representations, for each user, we apply a unique transformation, which has two properties. First, it does not lower the utility of the representations for the legitimate user. And secondly, applying those representations prevents the attacker from directly using representations from different accounts to train their stolen copy of the model. And those transformations are quite simple in their nature. I'm talking about affine transformation, padding or and shuffling. And we have also designed a transformation which turns the output of the encoder into binary form. So overall, those transformations aim to prevent sybil attacks, which are attacks from multiple accounts. Overall, the solution is the following. First, we calculate the representations, then for user queries, then we measure the coverage of the latent space for LSH. We map this coverage to a cost expressed through noise added to the representations, and to prevent a sybil attack, each user has a unique transformations with which we transform the representations before returning them to the user. And with a solution designed like that, b4b has many strong points. First, it causes no utility drop for legitimate users. As you can see, the performance of downstream tasks trained with linear layer on representations returned by the model defended with b4b and undefended is more or less exactly the same. Here we can also see that an undefended encoder is quite easy to steal. But when it's defended with b4b, the performance of the attacker drops significantly. And what's really important, the more queries they use, the worse performance they obtain. You see that the performance for 10 queries drops instead of increasing, as was the case for an undefended, as opposed to the undefended encoder. And finally, b4b successfully prevents sybil attacks from multiple accounts. And you can see that no matter the number of sybils no matter what number of sybils is used by the attacker, they are still not able to reach the performance of the attack of an undefended encoder, and well, the performance even decreases with the number of sybils. And in this scenario, an attacker is smart and adaptive, and they try to map those representations from different accounts to a single space, so break those transformations. However, even with such attempts, they are not able to reach the performance that they got when the encoder was undefended. So to sum up my presentation, so first, the important thing is the observation that for legitimate users, the queries from downstream tasks form separate clusters in the latent space, while the attacker must use diverse queries. And we can differentiate between those two types of behavior with this mechanism. Second thing is that we divide the latent space into buckets to measure how much of the information is extracted from the encoder. And we use adaptive noising to prevent a single attacker to steal the model. And in order to prevent the trick with sybil attack, we apply transformation, which make this kind of attack impossible. And in more broader terms, I think that the question of measuring what part of information is extracted from the encoder and in general measuring the coverage of latent space with queries is interesting research questions. And well, our framework is general, and you could potentially substitute buckets from LSH with another solution. And the same goes for transformations and noising. I mean, the cost does not have to be expressed through noise. You could, for example, have the user do some proof of work before returning the representations to them. And the higher the cost, the higher the work that the user has to do should be. And for transformations, we are also not limited to the one I mentioned. They just have to have those two properties. First, cause no harm for legitimate users. And secondly, be as hard as possible to reverse for the attacker. Thank you very much for your attention. And this concludes my presentations. If you have any questions, I will be happy to answer them.